Good day, colleagues. From Math 807, I'm William Groves, and this will be my final project. Question: can statistics save the ferry? A vehicle ferry carries trucks and cars across the river. This ferry can only accommodate one truck on the starboard side and two cars on the port side. An imbalance between the cargo weights on the port and starboard sides can cause instability. Given random selections of cars and trucks, we want to know the probability that the difference in cargo side weights in pounds is less than 2,000. We don't want our poor little ferry ending up like the picture. The weights of trucks follow a normal distribution with mean 10,000 and standard deviation 200. The cars also have a normal distribution with mean 5,000 and standard deviation 500. How lucky for us, they're normally distributed. Let's do some math. We have two normal distributions. Let's call them X and Y, which are random variables. X will be the distribution of truck weights and Y that of the cars. Let's think about what X and Y really are. These are not ordinary variables found in algebra. Here are histograms of randomly generated numbers that follow a normal distribution with the mean and sigma for X and Y. Look at all the information that we can gather just by writing the letter X and the letter Y. The random variables X and Y carry all this information. They carry a range of X values or Y values. And as we know, for any particular interval on the X-axis, we can calculate the probability of X being in that range. How are we going to handle this problem? Let's think of a specific example. What if we had a truck and two cars at the loading docks? We could call the weight of the truck X and the weight of the individual cars Y1 and Y2. Notice how we used lowercase letters for specific data points of a random variable. So for this specific case, we want the absolute value of X minus Y1 minus Y2 to be less than 2,000. This is trivial. When we have the cars and truck at hand, all we do is weigh them, get our calculator out, and we're done. But we want to know something about the future before the selection is made. We need the random variables because they carry the probability information. Gosh, could we follow this simple example and calculate a new random variable? Let's say A for answer. And A would carry all the probability information for every value of truck weight minus the two car weights, for every possible truck weight and car weight. That would be a random variable that would be very useful. But what does this mean? Well, note that this is not the same as X minus 2Y, and you probably find that very confusing. I will be glad to address that in the doctoral dialogue. All right, let's solve this problem. Here's the bad news. Combining random variables can be extremely complicated and in general requires convolution, a mathematical technique that has been the end of many a graduate student. The good news is that linear combinations of independent normal distributions, which is what we have here, are easy. So, given independent normally distributed random variables X and Y, we can define A equals X minus Y, and what we would like to have is that A is normally distributed and we know how to calculate the mean and the standard deviation. That would be the end of our problems, right? Well, a linear combination of independent normal random variables always results in a normally distributed random variable. That's good. And look at this. Here's how you calculate the mean. The mean of A is nothing more than the mean of X minus the mean of Y minus the mean of Y, very much like our formula A equals X minus Y minus Y. Wonderful. The standard deviation is not so straightforward to calculate, but the variance is very simple. Up in our equation, A equals X minus Y minus Y, you could think of X, Y, and Y having coefficients, where X had a 1 in front of it, Y had a minus 1, and the other Y had another minus 1. So look at our formula. The standard deviation squared, which is the variance of A, is that first coefficient 1 squared times the variance of X, plus that second coefficient minus 1 squared times the variance of Y, and then repeat it again. Ooh, that was easy. Note how the variance is added. Prove to yourself that variance X is equal to variance minus X, and you'll understand why they add, and I'll be glad to address that in the doctoral dialogue. So the mean of our random variable A is, mean of A is 10,000 minus 2 times 5,000 is 0. Wonderful. On average, they balance. The standard deviation of A is the square root of the standard deviation of the truck squared plus 2 times the standard deviation of the car squared. It ends up being around 735. The rest is trivial, right? We know how to calculate the probability of an interval on a normally distributed random variable. So we've reduced this down to a textbook problem. And what I mean is our textbook. We have a normal distribution A with a mean of 0 and a standard deviation of around 735. And all we need to do is calculate the probability that A is in the interval or is between minus 2,000 and 2,000. And that's just a matter of plugging it into SAS. And we find that there is a 99.35% chance that the imbalance will be less than 2,000 pounds. And of course, it's up to management to decide what happens when a selection of vehicles arrives and they violate that 2,000 pound restriction. Maybe they'll put them in a holding pen for a while, bring in some new vehicles, whatever, but it doesn't happen very often. How can we check this? How do we know that's right? Well, let's simulate the situation by generating 1,000 random selections of combinations of one truck and two cars. So literally, I've got 1,000 tuples out there. X1, Y1, Y2, the weight of one truck, the weight of one car, the weight of a second car. I do that 1,000 times. Then for each one of those, I take the truck weight minus the car weight minus the car weight, and we end up with 1,000 numbers. Now, let's see if we have a normal distribution. And let's see what the mean and the standard deviation are for those randomly generated numbers. Now, they were randomly generated, but according to a normal distribution, of course. Here's the histogram of X minus Y minus Y. That certainly looks normal to me. And it looks to me like the mean is right around 0. Maybe not exactly 0, but close. And we can see that the tails are out around 2,000, 2,100, 2,200. Okay, so 3 sigmas from mean, and our sigma was 735, so it looks plausible that the sigma and mean are about right. So let's get more detailed. Let's do a goodness of fit in SAS. Notice that test p-value is 0.855, which means very good fit to a normal distribution. Look at that line of dots. That looks really tight. Look at the mean. The mean's only minus 35, which is close to our theoretical value of 0. And remember, we're dealing with weights that are 5 and 10,000 pounds, so 35 is almost nothing. And the standard deviation is 725, whereas the theorized is 735. When you do random generation of numbers, you can't expect to come out with exactly the theoretical value, unless, of course, you generate a huge number of them. Here are some requirements which we were asked to fulfill for this project. In particular, to show the calculation for the probability that a continuous random variable is greater than a specific value, is less than a specific value, and is also between two specific values. I've already shown the case previously of being between two values. So let's take the case of the probability of A being greater than 500, which is nothing more than 1 minus the probability of A being less than or equal to 500, which is 0.24812. The SAS output is listed down below and highlighted. The other case is A being the probability of A being less than minus 500, which again is the same value because of the symmetry in the normal curve. Now let's keep in mind that the random variable A being negative means the cars weigh more than the truck, while positive means the truck weighs more. Generally, we don't care which cargo side weighs more, just whether they balance within the chosen limits. And we've already looked at the probability of minus 2,000 being less than the random variable, which is then less than 2,000. Here's the SAS code, which applies to the previous slide. We were also asked to find the values of the random variable for certain percentiles, which I've done here, 5%, 25, 50, 75, 95, and you can see from the SAS output the symmetry. This is the SAS code for the previous slide. All right. So colleagues, thank you very much for listening, and I hope to see you in the doctoral dialogue.